I'm Dr. Ken Lacovara, paleontologist and executive director of the Edelman Fossil Park of Rowan University, and I'm here to answer your questions from the internet. This is Fossil Support. Jenny Flyrocks asks, do you know how Tyrannosaur's head is too big for the rest of her? Is it me? Well, no, it's not you. It has a really big head. It needs a really big head because Tyrannosaurus rex in particular, had the strongest bite force of any land animal probably ever. And to have a really strong bite, you need a really big skull that can house really big jaw muscles. And it turns out that head muscles and arm muscles compete for attachment space around the girdle of the shoulder. So as T-Rex's bite got more ferocious, its head got bigger, its neck muscles had to get bigger. It needed to occupy more space on the shoulder for its neck muscles. Its arms got shorter and shorter and shorter. So those comical little arms that T-Rex has with two little witchy fingers is what made possible its murderous bite. Laura Bedrosian writes, can you comment on the science behind extracting dino DNA from mosquitoes in amber? Is that just Jurassic Park stuff? Yes, it is. Amber is actually a terrible geochemical environment to preserve DNA. People have looked, and no DNA from dinosaurs has yet been recovered. It seems to be too old, at least for existing technology and or samples. Clipped Wings 22 writes, how do fossil bones fossilize? Are they just filled with air, or are they somehow filled with the same rock that surrounds the fossils? The latter. They are filled with the same rock that surrounds the fossils. Here is a fossil pterosaur bone from Morocco. It's Cretaceous age. You can see that there is sediment inside the hollow bone of the pterosaur. And so what usually happens is the same rock that is surrounding the fossil also gets inside the fossil and it's preserved that way. Holton Music Man writes, how do fossils for fossil fuel end up 2 miles beneath the surface, especially enough to make oil? The fossils have to be buried in what we call a depositional basin. Think of a river valley or a continental shelf off of a coastline. As sediment accumulates in those basins, the weight of the rocks pushes them down. So they settle under their own weight. The pressure increases, the heat increases, and eventually those organics can turn into fossil fuels. Just Call Me Al asks, you know what's so effing cool? The evolution of discovering what dinosaurs look like through the years. Well, it's true. And our understanding of the way dinosaurs looked and behaved has been evolving ever since we discovered dinosaurs. When dinosaurs were first found in the early part of the 19th century, we didn't know what they were. Scientists didn't understand them. They thought they were these big, slow, lizard-like creatures. That's how they were first reconstructed. In 1858, the world's first nearly complete dinosaur skeleton was found in southern New Jersey, just 8 miles from here. And that's when we first started to get our view of dinosaurs as these vigorous creatures. But they were still constructed as these kind of living tripods. You always saw the bipedal ones with 2 legs on the ground and then their tail resting behind them to kind of prop them up. And then in old reconstructions, you see the giants, the sauropods, are always languishing about in swamps as though they couldn't support their great weight with their own limbs, that they needed the buoyancy of water. That's not true. The giant dinosaurs like Dreadnoughtus or Argentinosaurus were perfectly capable of walking on dry land with their 4 great limbs and holding their neck and their tail horizontal to the ground. One evolution that has happened just within most of our lifetimes is we can see it in the Jurassic movies. So in Jurassic Park in 1993, the idea that the meat-eating dinosaurs had feathers was really just emerging. So you see the Velociraptor, it's scaly and it's also very, very big. Velociraptor in life was lavishly feathered, a fully feathered dinosaur. And it was tiny. A Velociraptor skull is about that big. A Velociraptor is more like a pissed off turkey than a giant, monstrous dinosaur. If you have a Velociraptor in your kitchen, it's more of an opportunity than a problem. The Big Nasty One writes, how exactly is crude oil created from fossils? Having a hard time wrapping my brain around that biological process. Well, it starts with the smallest organisms. Some people think that oil comes from dinosaurs. Fossil fuel doesn't come from dinosaurs. It doesn't come from some of the largest creatures. It actually comes from some of the smallest. It comes from plankton, things like diatoms and foraminifera. And as they rain down from the oceans, or in deep lakes, the layers accumulate, and then they have to be buried. They could be buried by more organic material, or they could be buried by sand or mud, and then the pressure begins to increase, the heat begins to increase, and they start to cook, and they turn into what we call kerogen. Kerogen is a hard component of rock. It's the organic component. And if that is heated and squeezed in just the right way, it can turn into either petroleum or natural gas. Geology Johnson writes, what are the oldest fossil bones? Google says it's a 400 million year old fish. Are bones really that young? Geology Johnson, I really appreciate your deep time perspective, because while 400 million years may sound old to most people, it's really not. If you look at the history of complex life, the last 500 million years, that's only 1/9 of Earth history. And yes, it's true that the first ossified bones appear in the Devonian period about 400 million years ago. And the first function of bones was not to create skeletons. It was probably as a reservoir of minerals. If you're living in the ocean and the ocean chemistry is fluctuating from one state to another, you're going to have a tough time getting the minerals that you need to run your metabolism. Think of bones as a chemical battery for organisms. You can deposit minerals in a bone, and then later you can withdraw minerals from that bone. It's only later that bones start to serve the function of support as skeletons like we have today. The Stronk Orange writes, how do museums make the display models for their fossils, and how accurate are the displays to their fossils? I can speak best about what is happening here at the Edelman Fossil Park Museum. Our sculptor who did all of our recreations upstairs first starts with a 1/10 scale clay maquette of the creature he is attempting to reconstruct. And then he 3D scans it, and then he uses a CNC machine to print out slices of it. And that might be for a creature that ultimately is 55 feet long or so. And then all those slices are glued together, and then he puts resin or other material on top of it, and then sculpts the scales individually. He says, you just start at the tail and you start sculpting scales, and then a couple 100,000 scales later, you're done. And then it comes down to some really artistic judgments about it. What were the colors? What are the ornamentations? Were they shrink wrapped? Were they blubbery? A lot of that stuff we don't know, but what we do is we use modern analogs. So for example, upstairs, we have a reconstruction of a baby hadrosaur. Now, we don't know what color baby hadrosaurs were, but what we did is we looked at what color and what is the patterning of a small forest herbivore, and we looked at baby tapirs. So we gave it the colors and the pattern of a baby tapir, hoping that would at least get us a little bit closer to the truth of it. As far as the soft parts that the animals have, imagine like the coxcomb of a chicken or the wattle of a turkey. Those things don't preserve. And dinosaurs and other creatures must have had amazing and extravagant soft parts that we will never know about. A couple years ago, when the Apple TV series Prehistoric Planet was about to come out, the consulting paleontologist contacted me, and he said, we wanted to illustrate the point that there are all these soft tissue features that we may never know about. So I decided to give Dreadnoughtus pop-out air bladders in its neck. And so in the show, you see Dreadnoughtus, and then you see these pop-out air bladders. And he said, I'm sorry about this. It was my decision, and I realize you're going to have to answer the neck bladder question for the rest of your days. And that is actually true. Every time I give a talk now, I get the neck bladder question, and we have zero evidence that Dreadnoughtus or any other dinosaur had neck air bladders, but it is an illustration of the point that they probably had fantastic structures that will never be preserved in the fossil record. Dino 4x4 asks, what's your favorite example of convergent evolution? Well, convergent evolution means that organisms have landed on the same adaptation even though they didn't inherit those features from a common ancestor. So think of the wings of a pterosaur and a bird and a dragonfly. They all have wings, but they did not get them from a common ancestor. They evolved them independently because they were adapting to similar challenges. Think of the dorsal fin of a killer whale and the dorsal fin of a shark. Didn't get them from the same ancestor. You can see this in dinosaurs. You can see it in a creature like Spinosaurus, which has a crocodile-like skull. Not a crocodile, but it's a fish eater, as are many crocodiles. And so it's adapting to a similar situation. And so the evolutionary record in biology today is just replete with examples of convergent evolution. Caffeinated Caddy writes, did you know there's a dinosaur named Draco Rex Hogwartsii? Yes, that was named by a paleontologist named Robert Bacher. In this museum, we have a replica of a skull on display. Dracorex hogwartsii is a bit of a controversial dinosaur. There are many paleontologists that think it's actually a juvenile form of this dinosaur right here, called Pachycephalosaurus. Either way, whether it's a juvenile Pachycephalosaurus or its own species, it's incredible. It's an amazing skull. This thing looks like a dragon. Funked Up, that's Funked Up, asks, how would I give myself the best chance at becoming a fossil once I die? Well, you need quick burial, right? You can't hang around on the surface where you're going to weather away or become scavenged. You need to have yourself buried in what we call a depositional basin. So that's a place where sediment accumulates. Don't try this on a mountaintop because mountaintops are erosional and you will never ever turn into a fossil. To preserve flesh or soft tissue structures, you want to be in an anoxic environment, meaning one that lacks oxygen. That way the microbes won't decay the flesh. If you want to preserve the bones, you want a lot of iron in the system. So the iron that's dissolved in the groundwater can go through and mineralize out in the bones, and it helps stabilize the bones, and it turns them into a really resistant kind of material. Don't try to become a fossil in California or Costa Rica or in Iceland because those are tectonic or volcanic areas. You want to be in a place like the bayous of Louisiana or the pine barrens of New Jersey or maybe the swamps of North Carolina, places that are very environmentally quiet, so nothing is going to disturb that body as it's underground, sitting there for millions of years. Hughes Matt writes, how are dinosaurs' size and shapes determined from largely incomplete fossils? Anyone know the answer? Yes, I know the answer. It's true. Most dinosaur species are known from partial skeletons. So for very few dinosaurs do we have the entire anatomy represented. So what we do is we work with close cousins when we don't have a particular part of the body present. For Dreadnoughtus, for example, we only had 2 of the probable 13 vertebrae in its neck. And so to estimate the length and the proportions of its neck, we used a close cousin from northern Patagonia with the unlyrical name of Phytolachnosaurus. But that dinosaur was discovered with a nearly complete neck. And so we used that, and then we had very little cranial material for Dreadnoughtus. We just had a little piece of premaxilla and a single tooth. So we used another close relative that was known really only from a skull. Dreadnoughtus, on the other hand, has a nearly complete tail section. So other scientists that are working on this group called the titanosaurs, who find no tailbones or just a couple of tailbones, are probably going to use the tail of Dreadnoughtus then to fill in the blanks. And so we use close cousins whenever we can. It's me, Michael, writes, how do we know what dinosaurs ate exactly if only their bones were fossilized? Teeth, mostly teeth. We can really tell a lot about an animal's diet from their teeth. This is a crocodile called Thoracosaurus. It lived in the Cretaceous period. It was actually a survivor of the extinction, so it lived a little bit after the Cretaceous as well. But look at these teeth. They're not good for anything but murder. These little spikes here are good for piercing flesh, and you see the way they're curved back like a gaff hook. It's a fish eater, and so these teeth are meant to both puncture the fish's body, but also to keep it from swimming back out. So they all point backwards towards the gullet. If you look at a different kind of crocodile, this is a very rare crocodile. This one's called Bottosaurus. And look at this tooth. It has this blunt end, and this is a shell-crunching crocodile. It's picking up crabs and maybe snails and things like that and crunching them between these anvil-like teeth. Here's a little shark tooth that have serrations along the edge. So that is clearly meant for ripping flesh. So teeth are one way. Coprolites are another. Coprolite is a fancy word for fossil poop. We have a coprolite here. It's from, we think, either a turtle or a crocodile. And what you can do with these is you can slice them open and you can literally see this animal's last meal. So it's direct evidence of diet. We can also look at the isotopic signatures of teeth and bones. That can tell you what type of plants it was eating. It can tell you if it lived in a tropical or a temperate environment. And you can look at things like nitrogen isotopes, and that can tell you where it was in the food chain. And so we can tell if it was a prey species that ate only plants, if it was an omnivore, or if it was a predator. Next up, what's your favorite dinosaur? Well, I would say it's one that I discovered and spent about 10 years of my life working on, which I named Dreadnoughtus. And I say that because it really kind of became a member of the family. So much of our world for that time revolved around Dreadnoughtus. My son grew up with Dreadnoughtus. But I would say my favorite dinosaur that I didn't discover is Spinosaurus, which was found in the Bahariya Oasis of Egypt about 125 years ago. And it's this amazing predatory dinosaur. Think of a T-Rex, but kind of one that's been stretched out with a crocodile head, long arms with gaff hooks at the end of it. And then it has these huge 6-foot neural spines, which most people interpret as sails, could possibly be a hump as well. But this thing lived out in a mangrove ecosystem in what is now the middle of the Sahara Desert and ate fish, probably some big fish out there. I would say maybe, though, my favorite fossil overall is not a dinosaur at all, but it's one from the Cambrian period, from the high Rockies in Canada, called Pikaia. And Pikaia is a little tiny worm-like creature. It's about 1.5 centimeters long. It doesn't look very tough. It's soft and squishy, but it has some really interesting features. Pikaia has its sensory organs concentrated anteriorly. It has bilateral symmetry. It has a one-way digestive system, which I happen to think is the best kind of digestive system. It has V-shaped muscles. Does that sound like anybody you know? That sounds like everybody you know. And so if its descendants don't make it out of the Cambrian, there will never be vertebrate animals. There will never be fish or wombats or hoary bats or camels or dinosaurs or hamsters or you. Worthless Hope, first of all, that's sad, asks, which continents or areas are the best for finding fossil records, and why is that so? Well, it depends on what you're looking for. First, you need rocks of the right age. If you're looking for dinosaurs, don't look at rocks that are older than 237 million years old. You won't find dinosaurs. They have to be sedimentary rocks so that a fossil can form. You won't find fossils in an igneous rock or a metamorphic rock. And then today, not then, but today, it needs to be an arid environment so that you get good exposures of those rocks. That's why you usually see us paleontologists working in deserts and in badlands, because you can see the rocks. And especially in badlands, you get enough precipitation that it doesn't grow plants that cover the rocks, but there's enough water in the system to cause erosion, which pushes back the hillside, always exposing new bones. So you find those three things, and really you just walk until you see a fossil sticking out of the rock. That's how we do it. We never just dig a hole and hope to get lucky. We get ourselves in the right geological context, and then we prospect just by walking. Spector's Knight writes, what's the best preserved dinosaur fossil that's been found? Well, I would have to say Borealopelta from the tar sands of Alberta. This is a nodosaur, which falls in a bigger group, ankylosaurs, armored dinosaurs, and it was preserved in 3D. And so you can walk into a room with this dinosaur, and it's like you're in a room with a dinosaur. You can see the armor, the scales on this thing. It's just incredible. There's even some traces of pigment preserved, and it looks like it had what we call counter shading, like you can see in sharks and whales. So it was darker on top and lighter on the bottom. It's found in marine sediments. Even though all dinosaurs lived on land, oftentimes near-shore marine sediments do have terrestrial fossils. These are what we call the bloat and float dinosaurs. They die on a beach. They get swept out to sea. At first they sink, but the body fills with decay gases. They float out to sea like a giant rotten meat buoy. And as the carcass decays, parts of the skeleton start to drop to the seafloor. Jack D. Wiss writes, how long does it take to form a fossil? Not long. The organism has to be buried very quickly, and the bones have to be stabilized by minerals very quickly, a process that maybe only takes weeks or months. Because think about it, if it took a long time, then the processes of decay and degradation would destroy that carcass before it turned into a fossil. Vix Link writes, scientists study fossilized raindrops to learn about the Earth's atmosphere. Who ever thought raindrops could fossilize? It's amazing, isn't it? The geological record preserves the longest spans of time, but also sometimes almost the shortest spans. Raindrops can be preserved. Individual footsteps can be preserved. The landings of birds and pterosaurs can be preserved. Imagine how long it takes for you to make a footprint on the beach, right? Just a second. And if conditions are just right, that event that occurred for 1 second could be preserved for 100 million years. years. It has to be undisturbed naturally for a small amount of time. The chance of it happening is almost zero. But we get to do the experiment so many times, and deep time is so vast that even something that has an almost zero chance, but not zero chance of occurring, ends up happening a lot. There's a quote that I love that goes, "Unlikely things are likely to happen when happening happens a lot." Spiritual Pie 8298 writes, "How can we guess from fossils how animals and other creatures from millions of years ago lived, behaved, etc.? And can we at all?" Yes, we can. And more than guess, we can certainly see what kind of food an animal ate from its teeth and the way its jaws hinged and the way they were processing food. You can look at the feet and the hands. If you have an 8-inch sickle claw like Dryptosaurus, well, you know that thing is a flesh ripper and it was using that to eviscerate its prey. You're not going to see an 8-inch sickle claw on something that's eating salad all day long. You can tell a lot about an animal's lifestyle from its posture. Dinosaurs' feet are hinged for straight ahead forward motion. You know these were active, vigorous creatures. Contrast that with the languid, sprawling posture of something like a lizard or a crocodile with elbows and knees bent, belly touching the ground, tail dragging behind. A crocodile is always about a half a push-up away from taking a nap. Wetwork 76 asks, "Do you think all the dragon mythology was the result of ancient civilizations finding dinosaur fossils, or are dragons real?" Well, I don't think dragons are real, although there are some creatures like pterosaurs or Dracorex, a dinosaur, that look a lot like dragons. But I think what's really happening is that ancient people are encountering fossils. They don't have any context, they don't have any structure to interpret what they're seeing, and so they generate stories like humans do to explain their observations. There's a woman named Adrienne Mayor who studies folk paleontology, and she believes that the legend of the griffin, which has a lion's body and an eagle head, comes from observations of the fossils of Protoceratops. She also thinks that the legend of the Cyclops maybe comes from miniature elephants that used to live on the Isle of Crete. And if you look at an elephant's skull, they have their nose holes, their nares, coalesced together, and it's way up here, high on their head. It looks like it has a giant eye hole right in the center of its head, and thus perhaps the legend of the Cyclops. Ether Gorilla wants to know, dumb question, but why are mosasaur teeth so common? Not a dumb question, and we have some right here. In fact, we commonly find them out there in our fossil quarry. There are many more mosasaur teeth than there were ever mosasaurs. Mosasaurs had a lot of teeth. They produced them throughout their lifetime, and mosasaurs lived in places where sediment accumulated. And so when they would shed their teeth or when the whole animal would die and their skull would get buried, it was much more likely for those teeth to get buried, giving them a chance at turning into fossils. Tree boar rhubarb writes, "They also tell us the pterosaur, basically flying dinosaur, didn't evolve into birds, but the dinosaurs, basically non-flying dinosaurs, did evolve into birds, and they expect us to believe this rubbish." No. Please don't believe it, because science is not a belief system and science does not require your belief. However, we have a lot of evidence, I would call it a mountain of evidence now, that birds are in fact dinosaurs. We can see it in the evolution of their skeletons, and we can see it in preservation of feathers, actually, that go along with some of these skeletal finds, that the first avian dinosaurs evolved around 150 million years ago, and we have a really beautiful record now of the transition from non-avian to avian dinosaurs, leading right up to the birds today. A parakeet, a penguin, a ruby-throated hummingbird is a dinosaur to the same degree that a stegosaurus or a T-Rex is a dinosaur. Being a dinosaur, just like being a mammal, is a binary condition. You can't be half a mammal, you can't be half a dinosaur. Birds are dinosaurs. Pterosaurs, on the other hand, flying reptiles, not dinosaurs. It's a branch called Ornithodyra, and the ornithodyrans branched off before there was the first dinosaur. So they don't have a dinosaur in their family. They're not a dinosaur. News participant writes, "Do scientists have dinosaur DNA? Can you get that from fossils or?" We do not have dinosaur DNA. DNA is a water-soluble molecule, so it doesn't hang around that long in geological time. The oldest DNA that's been recovered from an individual is about 800,000 years old, and the oldest DNA from the environment is about 1.5 million years old. That sounds old, but that's a long way from dinosaur time, which is 66 million years ago. So we don't have dinosaur DNA, but what we do have are dinosaur proteins and blood vessels and some other biomolecules from dinosaurs. That's an ace. S, how big were dinosaur eggs? They were all little. This Giant dinosaur that you see over here, Dreadnoughtus, which I found in South America, that grew to be 65 tons, and its eggs would have been, no bigger than maybe an ostrich egg. All dinosaurs, when they hatched, were no bigger than about the size of a large house cat, and some were even a lot smaller. And I think that's actually kind of one of the secrets to the success of dinosaurs. Us mammals, we scale with adult body size. A baby elephant might be 300 pounds. A baby blue whale might be 6,000 pounds. But all dinosaurs start off small. So a baby Dreadnoughtus like that is in its environment, and it's doing tiny herbivore things at first, like rabbit-sized things. Then it's doing sheep-sized things and cow-sized things and elephant-sized things and then herd of elephant-sized things. So this one species is able to capture this entire column of resources from the ecosystem. I think that has something to do with the amazing success of the dinosaurs. Spooky Bite says, sometimes I think how tortoises and gators, crocodiles are so close to being dinosaurs and it makes me emotional. Look at them go. Well, I'm super glad you like turtles and crocodiles. I like them too, but they are not dinosaurs. Crocodiles are the closest living relatives to dinosaurs today, but they don't have a dinosaur in their family tree, nor do the turtles. And if you don't have a dinosaur in your family, you can't be a dinosaur. So they're living cousins of dinosaurs today. The only dinosaurs alive right now are birds. So if you love turtles and crocodiles, you should love birds as well, because they are dinosaurs. Miguel Wildlife wants to know how to know if a fossil was a juvenile or an adult. We can look at what we call the bone histology, where you can look at the bone cells, you can see how ordered they are, and you can plug that into a formula and you can get what we call percent senescence. So this giant dinosaur over here, Dreadnoughtus, when it died, it was 65 tons, but we got a real shock when we looked at the bone histology. We could see that at the time that it died, it was growing rapidly. We honestly don't know how big these things could get. Another way to do it is you can look at the anatomy of the bones. Some dinosaurs, like some hadrosaurs, are born in what we would call an altricial state, like a loopy baby robin, where the bones are kind of spongy, they're not quite articulated, they're soft, indicating that they must have received parental care. And then also, of course, if you have multiples of a species, you can look at the size and see whether that individual is old or young. X What's Good X asks, if the dinosaurs were annihilated by an asteroid, is there any evidence of the impact that's been discovered? Oh, yes. So the crater itself has been discovered. It's about 110 miles across by 12 miles deep. It sits off the Yucatan Peninsula in the Gulf of Mexico. There's also an ejecta layer from the fallout from the asteroid strike that's been found all around the world. When that asteroid hit, it blew the equivalent of about Massachusetts times 12 miles deep into near-Earth orbit, and that material then rained down all over the planet. To date, very few fossils have been found in that layer. There's some fish scales in Belgium. There's a mosasaur vertebra and a tooth in Poland. There's some paddlefish and a dinosaur limb in North Dakota. They appear to have spring pollen trapped in their gill rakers. So we think the impact happened in the springtime. We think it came in from the northeast at about 45 or 50 degrees. If you were on the Earth the day before the asteroid hit, you would have thought, well, this is how it's always going to be. These dinosaurs are always going to be on top. And then the next day, I think, they were functionally extinct from a cosmic accident. It's just incredible. It gives me shivers and makes me thrilled about the fact that I became a paleontologist. That's it. That's all the questions. Hope you learned something. Until next time.